It's been a great day so far. We've had 2 great presentations, and we've got another one upcoming. So buckle up. We're here for a few more, so it's going to be a good one. I wanted to thank our event sponsor, Verda Water Quality Systems, and our event collaborator, First Case, for our nursing credits. So thanks again, guys. It's been great to have you as a sponsor to the Verda team, and also First Case and Melanie Perry for providing those nursing credits. Also wanted to point out in the resource window once again that we do have a document that lines out the specifics on how to grab your CE, so please make sure to take a look at that. That really gives you a line-by-line instruction on how to grab those CEs. We have bonus CE content that's available, and we also have sponsor provided brochures and product information. And another quick thing as far as housekeeping is concerned, I know I mentioned this at the very beginning of the conference, but just want to reiterate, if you do have any audio or video issues, please just go ahead and refresh your browser. That fixes the issue probably 99% of the time. So if you do have those issues, please just go ahead and refresh your browser, and oftentimes, there you go, it's fixed. All right, let's get to it. Our next speaker is Tenley Miller. She is a water quality specialist at MMIC and Verda Medical Systems. She has over 20 years of experience in all aspects of laboratory operations, certification, and water quality analysis. In her role, Tenley works with SPD customers to assist them with water quality management and compliance with AAMI TIR 34. Her presentation title is Straight from the Pipe, Learning How to Manage Water Quality in the Sterile Processing Department. How you manage water quality in the Sterile Processing Department. Tenley is joining us to discuss the impact water quality has on SPD performance and success. So get ready to discover how AAMI TIR 34 helps facilities develop and maintain water quality assurance for SPDs. Let's take control of your SPD's water quality. Join me in welcoming Tenley Miller.
Good morning, and thank you for joining. We've already had some great presentations this morning, and I thank you for joining ours. Straight from the pipe, learning how to manage water quality in the Sterile Processing Department. Our agenda in this course is water quality impact on patient care, instrument life and equipment, water quality and surgical site infections, utility water, critical water, and clean steam, why and what to monitor, and why AAMI TIR 34 is so difficult. A little background, like he said, my name is Tenley Miller. I have a Bachelor of Science in Chemistry and was the president and owner of Reliance Laboratories until November 2021 when I joined MMIC and Verda. Reliance Laboratories was an analytical laboratory which specialized in water quality analysis, served the testing needs of multiple industries, including healthcare. I was involved in all aspects of laboratory operations, certification, and water quality since 2002. Prior to that, I was a laboratory technician in Reliance's lab. I currently am the water quality specialist for Verda's SPD customers, and like he said, I assist them with water quality management and compliance with AAMI TIR 34. MMIC Medical Systems introduced the first mobile surgery unit in 1996, pioneered the mobile sterile processing industry with the first and original mobile sterile processing system, or MSPS, in 2012. While providing the mobile sterile processing systems to facilities in need, we learned it wasn't always space and equipment that was needed for our customers. Water quality became more and more predominantly recognized as a need of sterile processing departments. While MMIC Medical Systems provided critical water to the MSPS that met AAMI guidelines, monitored the water treatment equipment, and provided the facilities with required monthly water quality reports, we strive to go beyond the water quality of the mobile platform. MMIC now introduces Verda, a comprehensive water quality system that can treat your hospital's water for sterile processing. We monitor the quality of water and the equipment function and provide hospitals with required reports to ensure AAMI compliance. So putting the SPD water quality into perspective. The performance of Sterile Processing Department has a direct impact on patient care, and the quality of the water used is an important aspect to the department's performance. 65% of infections treated in the developed world are due to microbial biofilms. There are many causes of microorganism formations on surgical instruments. Some are related to improper handling, such as scratches on instruments that can promote biofilm formation. Other is incomplete cleaning, can leave lubricants, particles such as surgical soil, lint, hair, fibers, glove powder on surgical instrument and inhibit cleaning. Also, too much time between the use and the reprocessing of the instruments can result in biofilm formation. Poor rinsing techniques can leave behind particles, soil, or detergents on medical devices. Poor quality rinse water can leave behind microorganisms, so many that decontamination and sterilization doesn't remove sufficient number to ensure that they're safe. What we're going to focus on in this presentation is the quality of reprocessing water and its impact on patient care. While high quality water by itself will not guarantee contamination-free instruments, it's one of many critical defense methods used when reprocessing instruments. Healthcare facilities employ a multiple of techniques, each defense method against microorganism growth. Each defense method has holes and exceptions through which errors and mistakes can pass, so individually each one is flawed. Imagine flawed method is like a slice of Swiss cheese, with the holes representing the flaws, allowing microorganism formation on instruments. If you put enough flawed Swiss cheese slices together, the holes don't line up and errors, that is microorganism growth, on instruments can't reach the patient. This doesn't mean any one defense method can be taken away. You can't skip soaking instruments or running the instruments through the washer disinfector. It's the execution of all cleaning practices and handling safeguards that ensure the sterile instrument success. So understanding how this affects patient care. The quality of the water used to reprocess medical devices will definitely impact your patient care. Ineffective cleaning, disinfection, sterilization can ultimately result in adverse effects on patient care. So too if bacteria or endotoxins are present in the final rinse water during instrument reprocessing. If there are high levels of total organic carbon, for example, this acts as food for bacteria, promotes bacterial growth. Bacteria and endotoxins on instrument, it just sounds bad, but what are the ramifications for patient care? For one, toxic effects. Tissue irritation can result from residuals on a device or implant that was reprocessed using water of inadequate quality. Two, pyrogenic reactions. Fever-inducing reactions could occur as a result of high level endotoxins and also non-endotoxin pyrogenic agents. Primary source is bacteria endotoxin. However, bacteria cell walls, staph bacteria, viruses, fungi, parasite components, other non-microorganism pyrogenic agents, some plastics and drugs, steroids, bile salts, they can also have pyrogenic effects. Any of these pyrogenic agents can be left as a residual from water that contained high microbial levels, or residual salts from water used from the final rinse could be converted by ethylene oxide to toxic residue. Most critically, patient infection can result from the use of contaminated devices. Salt or organic deposits from the water used in reprocessing could inactivate the disinfectant or sterilant, or could protect the microorganism from the disinfection process. A disinfected or sterilized device can transmit infection if rinsed with water with unacceptable levels of microorganisms. So, how big a problem is this? Surgical site infections occur in 2 to 4% of all patients undergoing inpatient surgical procedures. Although most infections are treatable with antibiotics, SSIs remain a significant cause of morbidity and mortality after surgery. They're the leading cause of readmissions to the hospital following surgery. Total readmissions are about 5.7%. Approximately 3% of all these patients who contact an SSI will die as a consequence. So obviously it's a huge, huge consequence that water plays an important part of. So the impact that the water has on instrument life. There are two impacts on instrument life due to water quality: contamination and malfunctions. So let's talk about the contamination. Poor quality water can result in spotting, staining, corrosion. All three can interfere with the sterilization. For example, where hard water spots exist on instrument surfaces, bacteria and biofilms can form and take hold. Stains are like spots, but tightly packed. The color of the stain gives an indication of the predominant mineral content in the water, such as copper or iron in the water. The color of the stain can also give an indication of too high or too low of a pH. Like spots, stains are surface regions, and bacteria and biofilms can form and procreate. Also, mineral deposits can act as seed points for corrosion to occur. The roughening of the instrument surface is where bacteria and biofilms can then take a foothold and be difficult to eradicate. It's more than having just good critical water for rinsing. Improper water quality for soaking and washing can also result in inactivation of the detergents or cleaning enzymes. This results in inadequate cleaning, which can provide surfaces on the medical device for microorganism growth. Whether it's from inadequate cleaning, corrosion, stains, or spots, if an accumulated biomass of bacteria can proliferate on instrument surfaces, they form biofilms, tightly adhered to the surface and not removed easily. The outer layers of the biofilm then protect the inner layers from destruction, eventually permanently affixed to the surface of the instrument. No amount of reprocessing or recleaning can make them decontaminated and sterile for reuse. Consequently, instruments, whether critical or semi-critical, require them to be disposed and replaced. So let's talk about some of the malfunctions due to water quality. For example, a hemostat may not open because of corrosion in the box area. Mechanical movement of the device could be obstructed by residual debris inside the mechanism. Corrosion could result in scissors and scalpels becoming dull and pitted. They won't cut with a sharp edge. Instruments then have to be resharpened more frequently, prematurely retired, adding to the cost of the department. Severe corrosion could result in surface stress fractures. Corrosion of a surgical instrument because of salt or other water deposits could result in breakage of the device inside the patient when stress is applied to the device. So let's look at the water quality impact on performance of the equipment. Performance of reprocessing and water treatment equipment depends on the water quality. For instance, improper water quality can result in inactivation of detergents and cleaning enzymes, causing inadequate cleaning. This is true for manual cleaning of instruments, as well as automated washer disinfectors. Water hardness, pH levels, total organic carbon, and temperature are some of the water quality parameters that affect the performance of detergents. Scaling pipes, valves, and sensors from hard water can cause faults, failures, more frequent maintenance, and downtime. Hard water scale also impacts the performance of water heaters and washer disinfectors, ultrasonic cleaners, and sterilizers with onboard boilers. Requiring more frequent replacement can ultimately result in damage, costly repairs if left unchecked. Endoscopy reprocessing equipment may also require some pre-water treatment for their feed water. Water treatment equipment often requires treatment to ensure optimal performance. For example, with reverse osmosis, high pH water will reduce the effectiveness of RO membranes, resulting in low-quality product water with too many dissolved solids remaining in the water to be used as critical final rinse. Likewise, tepid to hot water feed over 77 degrees Fahrenheit to the RO will result in degraded water quality. Lower temperature feed water results in higher quality product water, but at the sacrifice of product water flow rate. Chlorinated feed water damages the RO membranes, and if the chlorine level or the chloride level is high enough, the RO membranes wouldn't remove enough to meet the purified water requirements for final rinsing. And while not a water chemistry parameter, feed water pressure to the RO also needs to be maintained within the OEM specified range, usually no less than 20 to 25 psi. For UV irradiation systems, they often have pH, water hardness, ionic contaminants, TSS, total suspended solids, and turbidity requirements to ensure that the UV transmission through the water is adequate to destroy and inactivate the microorganisms. Final filters are intended to hold back bacteria and endotoxins from point of use. However, if the water has a high level of microorganisms, there's a greater chance for microorganisms to find their way through the filter media. There's a phenomenon not entirely understood, but studies indicate that given enough time, bacteria can grow, divide, move, even bend and conform to the shape of the microfabricated filter membrane to the structure and eventually penetrate through them. So what is AAMI TIR 34 water? It's clear that water quality is important. It's important for equipment performance and uptime, instrument life. It's important for patient care. It's so important that AAMI, the Association for Advancement of Medical Instrumentation, they created a technical information report, TIR, defining categories of quality water needed for medical device process, how to generate it, how to set up a quality program to monitor and maintain it. So what makes the SPS reprocessing special, and how is it different from facility water, which is likely coming straight from the municipal city water supply? Broadly speaking, water to be used in instrument reprocessing has been extensively treated to ensure that microorganisms, inorganic, and organic materials are removed. When we talk about microorganisms, we're primarily focused on bacteria and endotoxins, although fungi, parasites can also be a concern. Inorganic materials refer to minerals such as calcium, magnesium, manganese, chlorides, among others. There's a long list. Organic materials in sterile reprocessing can include bioorganic, dissolved, colloid, and aggregate organic matter. Some examples, soil or silt, clay, the decomposition of plant materials such as algae. Usually you're measuring total organic carbon in your water to check for the organic carbon. AAMI TIR 34 defines two categories of water quality, critical and utility. They use 13 different water quality parameters to define the critical and utility water, although 6 are given preferential focus. And slides. So critical water versus utility water. Let's define what they are and aren't, and why utility water is important and often neglected. When most healthcare facilities think about water quality for sterile reprocessing, they're thinking about critical water. So what is the critical water? Primarily, it's water used for the final rinsing of instruments. This could be during manual washing, ultrasonic cleaning, or in the final phase of an automatic washer disinfector. It's also used for dilution for liquid chemical sterilization equipment, depending on the OEM's instructions for use, the IFUs. And it can also be used for feed water for clean steam sterilizers, but more on that later. Critical water must be treated and conditioned. Municipal supplied tap water isn't of sufficient quality for final washer disinfecting rinses or for pure dry steam for sterilizers. Utility water quality standards aren't as strict. Processes like basic soaking, washing, and rinse cycles use utility water. Also, utility water used in the fill tanks in ultrasonic cleaners. Sterilizers use utility water, but only to temper steam drains and generating the Venturi effect to pre- and post-vacuum cycles. Unlike critical water, utility water doesn't necessarily require water softening, conditioning, or treatment. This is not to say no treatment is required. It just doesn't need to be extensively treated like critical water. For instance, it's common for water heaters to be fed softened water to reduce scale buildup on pipes, heating elements, and tanks. Some communities have water so hard and full of minerals it must be extensively treated and conditioned just to meet the basic sterile processing utility water needs. While in other regions of the country, no treatment of municipal water is necessary. AAMI defines there's 4 key qualities for utility water: the conductivity, hardness, pH, and chlorides. So here's utility water defined. This is Table 1 from AAMI TIR 34, and it defines the characteristics and specifications for utility water and critical water. Of all the parameters, the bacterial level is the one most customers are concerned about. Bacterial is important, and it's the one parameter, if not met, will result in shutdowns. But the other parameters should not be ignored. If you know, water hardness for utility water has to be less than 150 milligrams per liter. Critical water is less than 1. The critical acceptance level for hardness for critical water is so low, sometimes it's below the accuracy of test strips and below minimum reporting level capability of some water test labs. Also, some municipal supply water can exceed the 150 milligrams per liter for utility water, especially during different seasons as the water source changes. Conductivity levels provide an overall sense of organic and inorganic matter in the water. If the conductivity is low, then chloride, chlorine, iron, copper, etc., they're all expected to be low as well. Keeping the pH within specified ranges is important to maintaining optimal performance of the washer detergents and their cleaning capability. pH levels that are too high or low can also promote staining of instruments. Chlorides are the salts that result from chlorine gas combining with a metal. If you think about table salt is sodium chloride, that's sodium metal and chlorine gas. So chlorides will corrode even stainless steel instruments, and that's why it's very closely monitored. You know that for utility water, chlorides have to be less than 250, but critical water, they need to be less than 1 milligram per liter. Endotoxin monitoring isn't required on a regular basis for AAMI TIR 34 guidelines if the bacteria and the total organic carbon levels are within range, or if there's been no recent modifications or repairs to the critical water system. If there are modifications, there are plumbing repairs, then you need to test for endotoxins as well as bacteria after disinfection. This will change when AAMI releases ST108, the standard that is expected next year. Endotoxin testing will then be required either quarterly or recommended for monthly. As soon as the final release of that is available, then we'll be able to see what the guideline is. But it will be definitely at least a quarterly requirement, which is different from the AAMI TIR 34. And I do recommend reading the preceding pages after Table 1 in TIR 34 because there are other parameters that are recommended to be monitored that don't show up in this Table 1, like iron, copper, and manganese. Expected in 2023, possibly first quarter, maybe second quarter, AAMI, they'll issue ST108, which is the standard that will replace AAMI TIR 34. ST108 will include requirements instead of recommendations. The parameters to monitor will also increase from the list that's available in TIR 34. More parameters to monitor and more frequent monitoring. Why utility water is often neglected is that there's an assumption that utility water is the same as facility water. If your facility's in a region that's colored yellow on the map or light orange, then maybe you think the water hardness, it's not very hard, it's low, so we're okay. However, just as we've seen, water hardness is just one aspect of what defines acceptable SPS utility water. pH, conductivity, chlorides, bacteria, and endotoxin levels also need to be verified. The EPA regulations for drinking water are not the same as AAMI utility water specifications. So municipal drinking water may be in compliance, but still not meet utility water standards. Facilities management may be knowledgeable about drinking water requirements, but not realize these do not always meet AAMI regulations for water use in the SPD. If your facility is only softening the municipal water, that doesn't necessarily mean it's acceptable for utility water. Since water softening is an ion exchange process, you're replacing calcium and magnesium ions with sodium or potassium ions. The number of dissolved solids in the water hasn't changed. So the total dissolved solids and the water conductivity will stay the same. It's not uncommon for some regions in the country to have municipal city water that's simply too high of conductivity, even for the SPS utility water. It's common for municipal water treatment facilities to raise the pH of their water up above 9 or even 10 to prevent the leaching of lead from older pipes. Even if the pH is acceptable for utility water, say 8.9 for example, this is too high for RO systems and their purification performance is dramatically reduced. If the municipal water supply is on the lower end of the pH scale, say 6.1 for example, which is acceptable for drinking water, after RO treatment, the resulting pH may be too low. It'll be below the 5 to 7 range for critical water use, since extensive treatment removes the buffering contaminants and therefore lowers the pH. Bacteria in chlorinated municipal water is usually at acceptable levels. However, endotoxin levels may not be. Some medical device polymers can absorb endotoxins. Hence, the use of utility water in early reprocessing steps could result in unacceptable endotoxin levels because the endotoxins may not wash off readily in later steps. Total organic carbon is another water quality parameter that can fluctuate across the seasons, getting higher in the summer months. Think of algae blooms in summer water supplies, and can impact the effectiveness of detergents and promote instrument staining. Consequently, when we at MMIC talk about utility water, we're using capital U, the capital word utility, to indicate that it's a proper noun. And this is intentional to indicate that water is treated and conditioned to meet AAMI TIR 34 requirements for SPD reprocessing for utility water. It's not necessarily the same as facility water. If you refer to utility water with the lowercase, it's not a proper noun. People may assume incorrectly that the same water that's coming right out of the tap, and that may not be the case. Clean steam. So AAMI TIR 34 provides guidelines for necessary feed water quality for producing steam for sterile reprocessing. It's the same quality water as critical water. This can come in conflict with steam sterilizer manufacturers that require less stringent water quality parameters for their equipment to operate and to generate steam. So what should the SPS department do? AAMI TIR 34 is a guideline, is recommendation of best practices. It also has a standard ST 79 that states the requirements for sterile processing. And one of those sections delves into steam quality and steam purity parameters that must be maintained. While the acceptable ranges are not defined here, water hardness, iron content, pH, alkalinity are required to be monitored. And there's an argument that some manufacturers make that the boiler feed water that feeds SPS steam sterilizers doesn't need to be as stringent as TIR 34 outlines, and boilers' instructions for use supersedes any recommendation from AAMI. To that point, I'll assert the old adage, garbage in, garbage out, is an accurate assessment for steam sterilization. If you need to chemically treat your feed water and using steam filters to produce clean, dry steam, it nevertheless may not be sufficient to meet the needs for the sterile processing services. For instance, many healthcare facilities soften their municipal water supply, but they're unknowingly feeding treated water that's still too hard for producing high-quality steam for sterile processing. Water softened to between 4 to 16 milligrams per liter, which is considered soft water, the hardness will still accumulate, chalky spotting, and deposit formations over time. This results in more frequent sterilizer chamber cleanings and shorter lifespans on medical instruments. But even with ultra-low water hardness, feed water that's high in total dissolved solids and chlorides can still cause problems for instrument reprocessing. Staining, spotting, corrosion, wet packs, and incidents of bioburden are common challenges in sterile processing and are due to the quality of the sterilizing steam, which depends on the quality of the steam boiler's feed water. There's a long history in healthcare for the chemical treating of boiler feed water, incorporating steam filters, scheduling of boiler blowdowns to maintain the boiler equipment, and produce clean, dry steam. However, if the incoming water quality is deficient, then facilities will be faced with steam filters quickly building up contaminants, potentially clogging within days, increasing more frequent but less effective boiler blowdowns, and ultimately still chasing defects and dealing with frequent reprocessing rework in their medical device reprocessing. Clean steam is steam generated from purified water, most commonly from reverse osmosis filtration or deionization treatment. Instead of requiring multiple chemical treatments such as anti-scaling, pH control agents, neutralizing amines, or alkalinity builders, the purified water has significantly reduced contaminant levels, simplifying the water conditioning. Corrosive dissolved salts are removed from the steam feed water. Fewer boiler blowdowns and sterilizer chamber cleanings are required. Staining and spotting agents are eliminated. No residues are deposited by the steam onto medical instruments, eliminating potential sites for future microbiological growth once the instrument surfaces have cooled down. Dry steam ensures there's no wet packs at the end of the sterilization cycle. Microbial and pyrogen-free feed water results in microbial and pyrogen-free steam. Today's modern high-rated boilers are more sensitive to the quality of the steam feed water, and more steam sterilizers on the market now operate off purified feed water or clean steam. And with the sterile reprocessing steam only accounting for less than 5% of the total steam production for the average medical center facility, it may make sense to produce clean, dry steam for sterile reprocessing separate from facility steam. So water quality monitoring. AAMI TIR Authority 4 recommends monitoring both water quality at the point of use as well as after each water treatment step. The rationale is to ensure water quality is maintained and doesn't deteriorate over time. If water quality isn't maintained, the water can become contaminated with inorganic and organic contaminants, including microorganisms, and contribute to corrosion, staining, and increased microbial levels after reprocessing. AAMI Table 6 in TIR 34 gives an overview of water quality monitoring and the recommended frequency. Monthly testing for bacteria, also referred to as HPC or culture count testing, in the critical water is commonly tested and monitored by facilities. However, how, when, and where are important to ensure the testing is accurate and adequate. TIR 34 describes and refers to APHA's 9215, which is the American Public Health Administration standard for testing water for the HPC method. It includes information on how to draw the samples, for example, flushing the sample port for 60 seconds before drawing a test sample, the temperature to maintain the samples, less than 4 degrees Celsius, so samples are on ice if they can't be tested within 8 hours, and the maximum holding time for the sample is 24 hours. Maybe the testing laboratory's responsibility to ensure they meet all these requirements when sampling, but ultimately you're responsible and should be able to audit these test results and recognize why a particular sample result comes back positive for high-level bacteria if these criteria are not met. When testing, testing for bacteria immediately after a disinfection will give you a false sense of confidence in your water supply is free of microorganisms. TIR 34 recommends testing immediately before disinfection. Thereby, you're testing with the longest time period since the last disinfection. The where, typically facilities test for bacteria on one location, immediately after the reverse osmosis or the DI tank. And while this is important, sampling location, TIR 34 recommends also testing at the critical water point of use immediately after the last water treatment step on the return of the critical water recirculation loop and in the storage tank if one is used. By testing comprehensively, not only will you have confidence there's no bacteria growth in your water system, but if there is bacteria detected, you'll have more data to troubleshoot and pinpoint where in the system the contamination is likely occurring. If you notice, the endotoxin testing is only required after for initial validation and after any repairs or persistent bacteria levels. Total organic carbon is recommended for monthly or quarterly testing, depending on your site. pH is a test done monthly, and water hardness is recommended quarterly until a baseline is established, and then annually thereafter. In addition to the recommended monthly, quarterly, or annual testing, there are also daily testing and monitoring that is required. For example, the resistivity reading on any DI tank system is recommended to be monitored continuously with an audible, visible alarm when the resistivity drops below 1 megohm to prevent the inadvertent release of captured contaminants back into the water supply from the depleted DI tank. The feed water to boiler generating the steam sterilizers should be monitored daily. The testing can be performed manually or using inline meters to track the measurements. Some tests, however, should be performed immediately to maintain accurate readings. This includes pH and total chlorine. The recommended holding times for pH and chlorine is 15 minutes. So if you're testing for those parameters, those should be done on site immediately after the sample is collected. The longer those are exposed to air, the more inaccurate those results will be. Many facilities use independent testing laboratories to test water samples collected in the SPD. The results received from these outside labs need to be carefully interpreted. Testing on ultra-pure water, like critical water, has very specific requirements, and many typical lab tests are not optimized for these samples. Invalid results or inaccurate measurements can easily happen. Many laboratories are well versed in water sampling procedures. However, not all labs provide sampling services. Some use subcontractors. And not all, either the labs or the subcontractors have the necessary equipment for on-site testing for things like pH and chlorine as required. There are specific containers and sampling protocols for sampling purified water for AAMI compliance. Regardless, the person collecting the samples in the SPD needs to use proper techniques to ensure accurate results, especially when bacteria is being tested. Table 7 from AAMI TIR 34 describes visual observations that should be made by device reprocessing personnel on a routine basis, in many cases daily. The quality of water is important at each stage in the process and needs to be monitored. Table 7 lists weekly measurements of pH, hardness, and temperature for incoming water to automatic washers, washer disinfectors, AER, and ultrasonics. Note that the table also recommends observations or measurements be documented. Documentation is important to verify that the monitoring is done, to establish trends, and to indicate problems. Appendix B in AAMI TIR 34 gives methods for monitoring water quality treatment equipment. This ensures the equipment is inspected and maintained to give optimal performance. Monitoring can be done by maintenance personnel or reprocessing personnel. The water can be manually tested or measured using inline continuous monitors. Many options are available and will vary depending on the equipment that's installed. For example, Table B1 lists monitoring RO product water daily for resistivity or total dissolved solids using a continuous monitor. This is best provided using an inline resistivity meter that can be checked daily or that can provide the measurements electronically. There are also daily checks on total chlorine and water hardness. Again, the documentation is important to verify all monitoring for audit purposes as well as predictive measures to alert staff to problems as they arise. It's crucial to maintain and organize all these documents to demonstrate compliance with AAMI TIR 34 and upcoming ST 108. When it comes to water quality, it's not just one thing, but a combination of factors that contribute. It requires proper equipment, proper maintenance, and a program of regular testing and monitoring that all come together. Equipment needs to be appropriate for the facility's needs. The personnel need to be educated on proper performance and how it is monitored. A system of regular water testing and monitoring needs to be implemented, with someone overseeing the process as well as checking the results. You may not be able to rely on a commercial lab or a subcontractor, since there are different levels of knowledge and experience required for AAMI testing compliance. There are lots of people involved in water quality management, including facilities management, infection control, equipment maintenance personnel, and sterile processing personnel. So who has the ball? Spreading the accountability and responsibility of SPD water quality across multiple organizations can be a recipe for failure. SPD is responsible for testing the water at point of use, but not necessarily for fixing any issues. Water Maintenance Department manages the water feeding the SPD, and they're likely not educated fully on the requirements of TIR 34. The ranges of acceptability in the water quality parameters, how to address or fix problems when you're out of range. So how do you keep it all together? You need a multidisciplinary team of subject matter experts working together to manage the water quality program. You need people that know about the equipment. You need people that know about the maintenance and performance of the equipment. You need people that can interpret or explain water quality results. You need people that are collecting the water samples and doing on-site measurements. You have infection control and sterile processing personnel. Everyone on the team has a responsibility and purpose to maintain the water quality. We at MMIC have seen success at various hospitals when this team of individuals and departments, whether they're internal to the hospital or brought in from the outside like Verta, when they all work together. They meet on a regular basis to share information, they discuss problems, they make decisions, they go over their water reports, they go over the water equipment, they check the performance. The SPD is an integral piece of this group, and they need to have visibility into the water quality process. There are a lot of people involved in water quality management, but the SPD should begin to make a plan to be involved in the oversight of their program to meet the AAMI guidelines and keep the department running as it should. So in summary, a comprehensive plan of routine disinfecting, water sampling, water monitoring, and equipment maintenance is necessary for success. All of these things have to work together to successfully implement a water quality program. Water is the main ingredient of getting dirty instruments clean. Poor water quality can cause various problems with equipment, with instrument life, and ultimately with patient care. Critical water always requires extensively treated water and needs to be monitored to meet those guidelines. However, when talking about the SPD, most people are really focused on purified water or the critical water, and not a lot of talk about utility water. But the utility water quality could cause problems in the cleaning and sterilization process if it's not handled properly. The SPD needs to know the quality of their utility and critical water in order to do their jobs effectively. The only way to do that is to have a system in place for monitoring, piping sterilization, and equipment maintenance. What we see is an issue with many SPDs is just that they don't have a lot of control or visibility. Water quality is a multifaceted problem with many moving parts, and it needs to be tied together. SPD has an invested interest in this process, as we have seen that water quality greatly affects the SPD performance, greatly affects the patient care. So the SPD needs to take control of their own destiny, begin to get all aspects under one umbrella to manage the water quality. So that's the end of our presentation. Hopefully there's some questions to.
Tenley, that was great. Thank you so much. I really love how with your presentation and Tara's and Alpa's, there's a little bit of overlap, but there's necessary overlap because we need to be emphasizing these practices and processes, but you're all saying different things and really highlighting, high level on what we should be focusing on. And the other thing I really loved was your emphasis on the team approach to water quality management, because it's not, as you said, it's not just one person, right? You need a whole group to buy-in on the importance of this from the beginning of the process all the way to the end, whether it's facility operations, SPD, who's, at pre-treatment in the OR. There is a lot of involvement when it comes to water quality. And so, like you said, the team is the biggest part of this whole process.
Right.
We do have some questions, and one of them, it's actually from me, is that I wanted to, because since you're in the departments and you're advising departments on best practices and educating, and that's what we're here for, right? We're here to educate. What level of understanding of the scientific intricacies of water and water quality do you feel that sterile processing professionals need to have? Because you could really go into depth on the metals and everything that's part of what's, what encapsulates water, but what are the things that you feel are the most important?
Well, yeah, it is very important. And again, us at Verta, we feel that having a subject matter expert, having someone that knows about the water testing, someone that understands those water quality reports, someone that can present those to the SPD staff, to present those to the hospital administration, that is a very helpful thing for our clients. They don't necessarily need to focus on it. The person working in the SPD doesn't need to know about the water chemistry. They need to rely on someone that's making sure it's being done properly, making sure it's being tested, and then presenting it to them and giving them, an overview, making sure they're in compliance, giving them resources and ideas on how to fix problems before they happen or after they happen. It's generally our feeling that they should focus on their expertise. They should focus on their job. They should be, focused on patient care. They need to know it's being done, and they need to know that someone is in charge of that. But in general, trying to force a chemistry degree on everyone in the SPD is probably not the way to go.
Yeah, and I think it's a great point. I think it's more about understanding the overall importance of water and its role from, as we were saying, from the pipe all the way to the patient, and and having somebody that can really help push the importance forward. And then we talk about guidelines, right? And you really did highlight a lot of the nuts and bolts of TIR 34. But guidelines are sometimes open to interpretation. They're guidelines, right? They're not necessarily rules or regulations. So are there some specific areas within TIR 34? I know you highlighted those, but when you're in a department, are there, say, some areas that you really, really try to emphasize as far as like just baseline understanding of the document itself?
Mm-hmm. Again, my expertise is in the water, so I do always focus on water, focus on the utility water and the critical water and these parameters. But TIR 34 also goes over a lot of the plumbing, a lot of the development and creation of the department itself, of maintaining equipment performance and those kinds of things. So there's a lot of information, and we focus on various parts of it. And like you said, the AAMI TIR 34 is a guideline. When ST 108 is released and implemented, those guidelines will then be changed from recommendations to requirements. So a lot of this stuff that AAMI is just recommending or giving guidelines on will then become a requirement of all the SPDs. So the department will have to make the those changes, have to implement those quality systems, have to implement the water sampling and the documentation to make sure that they are in compliance with ST 108.
Yeah, that's a great point. I think, it's starting now, start the process now and start best practices and really start to hone in on that importance and get the team buy-in, because when it becomes a regulation and a rule, then, you're going to be held to it. So that's a great point.
Right.
This one is a good question, I think, that will probably tee up for the conversation that we got coming in the next panel discussion. But what additional concerns should SPD consider when it comes to flooding conditions in the community, such as hurricanes, flooding of rivers or city streets, which can cross-contaminate in the water treatments? Are there safeguards, I guess, is what's being asked on this end?
Yes, there are. Again, one of the main things you can do is to be vigilant in your monitoring, to take those water samples, to know the quality of the water coming in to the facility, to coming in, making sure that you are checking that water, so that you monitor any changes to the water supply that's being sent into your department. And if you have that, then you'll be able to see when changes happen. You'll be able to detect when there's bacteria in the water, or over dissolved solids increases. You can find those things right on the spot. You can find out as soon as it happens, and then you have to make changes, or just implement new monitoring or new equipment or something if it's necessary to take care of those problems.
Great. Yeah, and this one, this comes from the same person, which is Ann Mattern. She is also asking about the concerns when there is a lack of municipal water or even lower water pressure. And I know Tara talked about in her presentation the importance of having a free-flowing system to have continuous water movement and that it's not sitting dormant. So are there any points on that front that you'd like to address or talk about?
Well, yeah, there are. Again, with MMIC, we have engineers that work on those types of things. So whether it's MMIC or another consultant or someone that's working on it for you, if water pressure is an issue, then yes, there are ways you can mitigate that you come up with a system that will still meet AAMI compliance, address the low water pressure issue. And that's, again, just one of those things that a good engineering or designing of the department up front can help you understand what you need, what works for your facility.
Great. All right. Well, so this is a big picture question, and I'm sure that you run into it a fair bit. And, say if you have a facility that you're working with or that you've consulted with, and they're considering implementing a water quality management or monitoring program, and they've not done it. Mm-hmm. What are the steps that you take to help guide them through kind of implementing this process?
Well, the first step, again, is to take a look at your department, to take stock of what you have, what monitoring or what is available already. What is your facility doing? What is the municipal water supply doing? Always start with a water test, obviously the supply that's coming in, and then go through your department and take stock of where you are. See what needs to be done, what changes do you need to implement, to get from where you are here to where you want to be with compliance. And again, there's people like us at MMIC. There are other people that are experts in this. Some of the people that work in your facilities may have a lot of that information as well. Again, it's a team effort. You put those people all together. You find the people that know what they're talking about when it comes to the water quality, and get information from them to make the changes you need to get where you need to be.
Right. Well, and I think another good point is this is a continuous process. It's not just a plug and play and you walk away. Once it's implemented, it requires continuous testing, as you pointed out. It requires monitoring on a daily, monthly, annual basis. It's like, here you go, guys. We're going to give you this program, and we'll see ya. I think it's a wide-ranging involvement, as you talked about, with the team and making sure that there's buy-in across the board. So I do appreciate.
It's definitely an ongoing process.
Yeah, for sure. Well, I will give you a breather because I know you're going to be hopping on for the next session with Bobby for the panel discussion. So, Tenley, I really do appreciate you presenting and providing some insight on your background and what you do to help the facility succeed in a water quality management program. And so, and also just your insight on TIR 34. That's some great stuff on that end as well. So all of you out there, we've got a few more sessions to go, but really appreciate you joining us today once again. And we will be back here in about 14 minutes with a great panel discussion. So stick around. You're not going to want to miss this one. Thanks again, Tenley, and we'll see you soon.
Thank you very much.